Hello everybody, let's take a look at a problem, and it's going to involve equilibrium, it's going to involve displacement vectors and force vectors and unit vectors. Okay, so here's the situation. I've got a car stuck in the snow over here, and I've got 100 feet of rope, and I've taken part of that rope and I've attached it to the car, and the other end of the rope I've attached to a tree. All right, and then I'm pulling on the rope. Now, ideally, I would not pull it in this scenario, in this set of angles, but let's just go with it the way it's drawn. So I'm pulling with some force P over here, and then there's a tension in the rope. There's a tension on the 70-foot length, okay, so 70 feet of rope goes from here, the origin at the tree, to where I'm pulling, and then there's 30 feet of rope going from where I'm pulling to the vehicle, the car that's stuck in the snow. All right, so first off, I have a displacement vector from the tree to where I am pulling, and I'm going to call that R70, and that's going to equal 70 feet, and the angle that I'm going to choose to have down here is 65 degrees, okay? So we'll assume that that's given in the problem. So 70 feet at an angle of 65 degrees. And of course, that's 70 feet cosine 65 degrees in the I plus 70 feet sine 65 degrees in the j hat direction. All right, so there's the polar form, and then this is the Cartesian form. And if I calculate out that Cartesian form, I'm going to get 29.58 feet in the I hat direction, and I'm going out as many significant digits as I feel are reasonable. My calculator's got all of them, and I'll round it off at the end to what I think is necessary based on the significant digits I'm given in the problem, right? And then 63.4 feet, 63.44 feet in the j hat direction, right? So there's that. Now, I also have 30 feet, and I'm going to say that this angle in here is 110 degrees, right? So that's into the second quadrant like it should be, right? So that's 110 degrees. And so I'll call that R30, and that'll be 30 feet at an angle of 110 degrees. And if I calculate all of that out, I get minus 10.26 feet in the I hat direction, so it's going left like it should, and then 28.19 feet in the j hat direction. All right, so there's my displacement vectors. One from the tree to where I'm standing or pulling on the rope, excuse me, I'm not pulling on the car because I'm not touching the car. And then from me to where the car is located and the rope's going in that direction. Okay, now, in order to do this problem, I'm going to pull on this vehicle, and I'm going to say I'm in static equilibrium to make life simple. I'm interested in the forces, this T70, so that's the tension in the 70-foot length of rope, and then the T30, that's the tension in the 30-foot length of rope. And I'm going to be pulling with some force P, and right now that's not designated, but we'll designate it before it's all said and done. So these are my three force vectors, but notice the T70 is down and to the left. So the R70 was up and to the right, so when I do this problem, I want to go down and to the left, okay? So I've got to take minus the R70. So what I want is, when I do the sum of the forces vector, I'm going to get T70 times negative R70 hat, because it's in the opposite direction as the R70. And then plus T30 times R30 hat. And then finally plus P, which is all in the I hat direction. And so all of that's going to equal 0, right? I'm going to assume that I'm pulling P in the X direction. I can designate that because I can make the axes whatever I feel is necessary. Okay, now remember that R70 hat is equal to R70 vector, which is right here, divided by the magnitude of R70. So vector, but magnitude. Well, that's pretty easy. If it's 70 feet of rope, R70 is 70 feet. So in a similar situation, I don't want a plus. In a similar situation, R30 hat is equal to R30 vector, R30 vector over 30 feet. So notice R30 vector is going to be in feet, and I'm dividing by 30 feet. There will be no dimensions, no mass, length, or time here. So this is a unit vector. It has a magnitude of 1. Not 1 foot, not 1 meter per second, just 1. Okay, and so what I'm going to do is I'm going to substitute these values into this force equation, right? And I'm going to calculate out the tensions, okay? So when I do that, I'm going to end up with, I'm going to take the 29.58 and I'm going to divide that by 70, so 29.58 feet, right? I'm going to divide that by 70, and then 63.44 feet. I'm going to divide that by 70. This would be in the x direction, this would be in the y direction. But this will be negative, right? Because it's going down and to the left, the force is. This is up and to the right, but the force is in the opposite direction. It's down and to the left. Okay, so let's do that. So the sum of the forces, and I'm just going to do the x direction first. So I'm going to get 29.58 feet divided by 70 feet times T70. That's just the magnitude, but remember that's going to be down and to the left, so that's negative, right? And then I also have minus 10.26 feet. That's the x component of T30, so I have to divide that by 30 feet. So you'll see the feet are dividing out. And then, remember, P was to the right, so plus P, and that's equal to 0. And then the sum of the forces in the y. Okay, in the y direction, I had 63.44 feet for T70, or for R70. And so I'm going to divide that by 70 feet and multiply by T70. And then for the, and that's down, right? So I've got to put a negative sign out there, right? Because it's in the opposite direction. And then I had 28.19 feet. And divide that by 30 feet. That was R30. So I multiply that by the tension. So this is now the unit vector component, the x direction or the y direction unit vector, and then that's all equal to 0. All right, and so my unknowns, I've got T70 and T30, and I'm going to designate then P to equal 100 pounds. Right, and so what do I have? I have 2 equations and 2 unknowns. All right, so you can find out what these are. You can put that into a calculator and figure out what those are going to be as far as decimal places. And I just use several decimal places. I let my calculator hold all of that information. You could also do it on MATLAB or Excel, something like that. But if I solve this out then, 2 equations, 2 unknowns, I get T70 then is 133 pounds. And T30 is 128 pounds. Okay? And so you can see that even though I'm pulling with a force of 100 pounds, I'm pulling on the car with a little bit more force at 128 pounds. It's an interesting problem physically. I wouldn't set it up the way you see here. If you really wanted to do this well, the way I would run that is there's a rope in here between the car and the tree, and then I pull on that rope, and it turns out that I can pull with a force of about 100 pounds, and the tension in this rope can be very large, hundreds of pounds, if not more. It just depends on the angles that I'm working with. I'm not going to work that problem, but that might be a neat one for you to do on your own. But you'll find if your car is stuck in a ditch and there's not a tow truck nearby, but you happen to have some rope, attach one end of the rope to the tree and the other end of the car, make it super tight so this is almost straight, and then just yank on that and keep the angle small. And you can exert a very large force on that car. And I hope you don't break the rope, as a matter of fact. All right, so that's unit vectors and forces multiplied by unit vectors in 2 dimensions. We've also gone from polar form to rectangular format, and then figured out how to do the unit vectors, and then finally wrote out the force equations, the equilibrium force equations, to solve for whatever unknowns I'm working with. All right, so I hope that gives you a pretty good idea of how to work this problem. If you have any questions, please leave them in the comments below. Thank you.